Hello, my name is Hyunsoo, and today I'm going to present our work if templates. So diffusion models deliver incredible generation quality, but they are too large to run on custom-level GPUs. As you can see in the chart, the VRAM requirements far exceed the available memory. Therefore, we need lightweight models that have a low computational cost. Training a lightweight model from scratch often leads to suboptimal performance and unstable convergence. In practice, we usually compress a large model via quantization or pruning. On top of that, knowledge distillation enhances performance by transferring knowledge from the large teacher model to lightweight student model during training. In this work, we focus on knowledge distillation for lightweight diffusion models. In context of KD for diffusion models, we use out KD and bit KD to match noise prediction and intermediate features respectively. While prior work shows KD improve performance, the underlying KD mechanism remains largely unexplored. In context of KD, we discuss the capacity gap, the motivation for our work. Intuitively, we expect that the stronger teacher with large capacity would lead to a better student. However, when the model size difference is too wide, the student fails to mimic the teacher's complex behavior. Actually, our empirical analysis shows this capacity gap problem in diffusion models. We observe that as teacher size increases, student FID goes up with a larger standard deviation. So we define problem is that larger capacity makes weaker performance and less stable convergence. To address the capacity gap, prior works use weaker teachers or intermediate checkpoints to simplify knowledge. However, this approach prevents us from fully utilizing a strong teacher's rich knowledge. To fully utilize teacher's knowledge, we analyze the distillation error using regression-based correction during the noise process. At each time step, we estimate coefficient per sample to correct the student's predicted noise. This correction significantly improved the performance. This indicated that there are distillation errors that can be corrected with low order moments alignment. We define this as the distillation error. However, a performance gap still remains compared to the teacher. This is the hard distillation error, which means nonlinear residuals that are not captured by easy alignment. This implies that conventional KD does not run both easy and hard distillation error. Therefore, we assume that equally minimizing both errors makes training unstable. So, we propose easy to hard training strategy that aligns the easy error first, then refines the hard error. However, applying this regression-based question is not practical because the teacher network is unavailable during inference, and separate coefficient estimators add extra overhead. Therefore, we propose a method that a student model implicitly learns these coefficients. So we first parameterize KD objective via simple linear regression. This parameterization gives us easy and hard decomposition. In training time, we cannot directly satisfy this constraint. So we regularize this coefficient with this easy alignment regularization. Closed form solution of OLS enables this regularization. Note that we estimate this coefficient per sample in data batch. And the hard refinement defined as residual gap between teacher output and student corrected output. This minimizes these fine details errors that are not captured by regression. Based on this decomposition, we adopt an easy to hard training strategy using an adaptive weight omega. As the easy loss decreases, the hard loss is more emphasized. This naturally drives our lift loss into an easy to hard training strategy. However, as the left graph shows, simple linear regression cannot fully explain the data point, meaning a single set of coefficients in lift is insufficient. Therefore, motivated by piecewise regression, we divide the output and estimate separate coefficients for each group. This provides a more reliable coefficient estimation and effective alignment of lift. However, diffusion model outputs are high dimensional. In this case, there are two naive approaches include flattening and patchifying. However, these naive approaches do not consider spatial information. Moreover, we observe that distillation error is spatially non-uniform. As shown in the figures, error is non-uniform across diffusion time steps and training iterations. This motivated us to perform dynamic grouping for each training step and data samples. Therefore, we propose place that is error map-based adaptive grouping strategy. We define difficulty using the error map, group it by magnitude, and calculate the lift loss for each group. Therefore, our praise make adaptive grouping in data and training iterations. Finally, our overall training objective combines the diffusion loss, our lift loss, and the feature level distillation loss. This brings us to the end of our method. To validate its performance, we show experiment results. Our experiment used a pruned student model as initialization. During training, we simply replaced outcade with our lift and place. On the salary data set with default pruning, our method achieved a stable convergence even for the extreme right student model in the red box. We also evaluated on the complex L-sum bedroom data set. Specifically, our method at 70% pruning ratio, even outperforms conventional KD at a 50% pruning ratio. Our method generalizes well to various backbone data sets and flow-based models, which you can find it in our paper. When distilling from teachers of various sizes to a fixed student, our method shows consistent performance gains. Interestingly, our framework achieved the best performance when distilled from the strongest teacher. In summary, we highlight the performance drop caused by the capacity gap in KD for diffusion models. To address this, we propose a lift to decompose the objective into easy and hard components and praise for locally adaptive error-based grouping. Our framework is architecture and task agnostic with no extra parameters or inference overhead. Thank you for your interest in our paper. You can visit our project page via the QR code.